Bismillahirrahmanirrahim. Assalamu alaikum, dear students. We are now starting the second lecture for week number 8 for wireless and mobile communications. In our previous lecture for this week, we talked about the multipath propagation, and we discussed that there is an important phenomena associated with multipath propagation, which is represented as the delay spread. Different rays which are coming from the different propagation paths, they reach the receiver at different times, and because of the reception at different time, there is a spread which is associated with that delay. This temporal spread which represents some expansion in the time width of the wave, is generally measured in terms of the delay spread. We also discussed that this delay spread is actually represents the standard deviation of the delay, which is associated with different components of the wave. So we continue the discussion on this thing, and now we would look at the other perspective of the same phenomena, which is the frequency perspective. Delay spread is actually represented in time domain. So basically delay spread is calculated with reference to the time axis, but we know that there are two different views of phenomena or signals which we see in communication system. We either represent the signal in its time domain, or we represent the signal in a frequency perspective. So what is the effect of having delay spread on the frequency components, and how does this spread would be represented in frequency domain? So this is the topic of today's lecture. So let us start our discussion. From frequency perspective, the channel is divided into two categories. First one is flat feeding channel, and second one is known as frequency selective channel, which we'll be discussing in a while. So we start our discussion with the flat feeding channel. So what does flat feeding channel mean? Say for example, we have a channel which is represented by its impulse response ht. Of course, this impulse response would have this form, as we discussed in our last lecture as well, that each component would have some delay, there will be some phase change, and there will be some amplitude response associated with each component. If we apply a pulse onto this channel, so we will get some output. So it is represented somewhere here. So we would see that there would be some output that will be received on the other side of the channel, or at the receiver side. Generally, we experience some sort of distortion in time domain. It's common that when the signal propagates through the channel, there will be some distortion, but the point is whether there is some significant delay there or not, or whether there is some elongation in the signal or not. In frequency domain, we represent this thing in terms of a bandwidth. We say that a channel is a flat frequency response if its frequency response is almost constant in the signal bandwidth. Frequency response, let me show you the next slide here. The previous figure was presented in time domain, but this one is the frequency domain version. So we have some signal which has a bandwidth which can be represented from first lobe of the signal, say this one, and there is a frequency response here, but you can see that in the region where the signal bandwidth exists, this frequency response appears to be almost constant. So this channel has an almost constant response in the bandwidth of the signal. In other words, the channel is flat if the frequency response is almost constant over the frequency level of the input signal. So if because the response is constant, if any signal is applied to the channel, the output signal bandwidth would remain same as that of input signal bandwidth. So there will be no change in the bandwidth of the signal. The output signal bandwidth would remain almost the same. So say for example, you can see here, this is the input signal and we have a flat frequency response represented by HF, and the output frequency response remains same. There may be some change in amplitude as we discussed, because channel associates with some change in the frequency amplitude and phase, but the bandwidth, which is represented here, bandwidth is almost same, which is represented by the input signal. So how does this response relate to the delay spread? Actually, the channel also has certain bandwidth. The channel, as we discussed previously as well, channel behaves like a filter. So channel also has certain bandwidth, and that bandwidth is represented in terms of the delay spread, which is Tm, and this bandwidth is approximated as 1 over Tm. This delta Fc is known as channel coherence frequency or channel coherence bandwidth. So what is a coherence frequency? Coherence frequency is that particular band of frequencies where you would see that the response, the channel response is almost constant, or in other words, the fade amplitudes, they are highly correlated to each other. So one fade amplitude would be dependent on the other, so you would not see uncorrelated fades in that particular bandwidth. So mathematically this bandwidth is characterized by delta Fc, which is reciprocal of the delay spread. Okay, so what is the relationship between the channel coherence bandwidth and this input signal bandwidth for a flat fading channel? As we discussed that for flat channel, the signal bandwidth does not get affected by the channel. In other words, the signal bandwidth should be smaller than this overall coherence bandwidth of the channel. Coherence bandwidth is large as compared to the signal bandwidth. So this signal bandwidth should be smaller than this coherence bandwidth. If this condition is satisfied, in that case the channel would be characterized as a flat channel. The signal bandwidth is generally represented by 1 over Ts, and the coherence bandwidth is represented by 1 over Tm. So I can write 1 over Tm should be greater than 1 over Ts. So we get a simple relationship in form of time domain as well. The signal time duration should be greater than the delay spread of the channel. So for the frequency flat channel, the flat faded channel, we would see that the signal bandwidth, signal time duration is significantly greater than the delay spread. So for such channel, the channel frequencies would not affect the signal frequencies. So this type of channel sometimes named as the frequency non-selective channel. In non-selective channel, as the delay spread is significantly smaller, so we conclude that the different signal components, they arrive at the receiver with almost same time as compared to the signal time. So the delay in the different components is significantly smaller. So different components can be taken as they are arriving at the same time. So in that case, channel response can be simplified in the following manner. For example, this is the general channel response that we discussed, because there are n different components or n different multipath components that are available. Each component has some amplitude associated with that, some delay associated with that, and some theta, and the phase angle is associated with that. So because all the components are taken as arriving at the same time, so I can say that I can replace this tau n by a constant number tau naught, which can be taken out of this summation. It should be delta here, sorry, it's a typo. So you would see that this component, this part, is actually representing the overall change in amplitude. ANs are representing the amplitude and theta n representing the phase. So of course, when these components would add up, so there will be a resultant phase and resultant amplitude. So we can replace this entire summation with a resultant amplitude and phase. So this summation is replaced by a e raised to r j theta, which generally refers to fade amplitude. A is actually representing the fade amplitude, and theta is the received phase angle. So this can be simplified in following manner. So delta ht can be represented that it has some amplitude and some phase associated to that, and of course there is no specific delay associated to individual component as compared to the signal duration, so we can ignore that thing. So this is the overall impulse response. So we have only two different significant components, that is amplitude and phase. Typically the amplitude follows the Rayleigh distribution, Rayleigh random variable, and the phase follows the uniform distribution or uniform random variable. Okay, so this was the discussion related to the frequency flat channel. Now let us take the second case where we have a frequency selective channel. Frequency selective channel is actually reverse of that case. For frequency flat channel, we discussed that the signal duration should be greater than the delay spread. So if we have a reverse case, that is the signal duration is smaller than delay spread, or signal duration is almost same as the delay spread. So what happens in this particular case? In that case, the coherence channel bandwidth would be smaller, delta fc would be smaller. That results in a frequency selective channel because of having the smaller bandwidth as compared to the signal bandwidth. Let me show you the diagram for that here. So say for example we have a frequency selective channel which is represented by this relatively smaller bandwidth. So the filtering effect of the channel is actually restricted to some specific frequency band, which is represented by the frequency selective nature of the channel. So if the input signal is applied to the signal system or channel, so say for example this is our input signal which has larger bandwidth as compared to the coherence bandwidth of this channel. In that case, the output bandwidth would be restricted to the channel bandwidth. The signal bandwidth will be truncated. It will be changed to that particular signal bandwidth. You can think of the channel as a filter. So say for example the filter pass band is this one. So whenever this signal goes through this filter with a smaller pass band, the output would be restricted to the pass band only, then stop band part would be eliminated. So eventually you would see that there is a significant change in the signal bandwidth. There are certain components of the certain frequency components of the input signal that would be truncated at the output side. The above figure is actually time version of that same frequency selective channel. So we have a frequency selective channel here, and we applied a pulse onto that frequency selective channel, because the channel would truncate different frequency component. So you would see a significant amount of distortion in the signal, and as we discussed that the delay spread is large, so there you would see a spreading of the signal in time domain as well. So the signal would be replaced by a spreaded version in time domain. So it's a distorted and spreaded version in time domain that you would see when the signal passes through a frequency selective channel. So let us go back to the mathematical form. So in this particular case, the output signal would have smaller bandwidth as compared to the original transmitted signal, because the channel has truncated the bandwidth and limited the bandwidth to that particular coherence frequencies of the channel. So the channel becomes frequency selective in the sense that at certain frequencies it will allow signals to pass, but other frequencies will be stopped by the channel. So it's actually filtering out some frequency components. So in this sense, this channel is named as the frequency selective channel. So in that case, different components they would have different impacts. We cannot ignore these delays of the component. So the overall generalized expression will remain same as we discussed before. So there will be different components that will be arriving at the receiver side with different delays and different phase angles and different amplitudes. So we would have to include all those effects in our analysis. So let us discuss how we generate or mathematically or practically calculate this type of spreads. So if we take the measurements generally, so we get a number of measurements which are generally represented as sample delay profile, which is illustrated in this figure A here. You can see, so signals coming from different deflections, they arrive at the with different amplitudes and as well as different delays at certain points. So you can see that the signals coming from different types of scatterers, they are arrived at different times. So this bunch of signals, they are coming from one scatter, the other bunch is coming from the second, and so on. Let me quickly show the previous figure that I represented in the last lecture as well. So you can see that, so the rays which are coming from this scatter, they will be grouped in one sample delay profile. The rays coming from the other one would be represented as a group in the other sample delay profile, and the multiple rays which are coming from the third scatter would be grouped as a sample in the sample delay profile, and so on. So different rays coming from the different scatterers, they eventually have a minor delays and almost same amplitudes with each other. So typically for analysis purposes, we generally combine all those groups into a single representation. So how do we do that? So this is the representation here. You can see that the multiple samples which are coming from one type of scatter, they are grouped here. So we we calculate the average effect of this thing and represent as a single ray, so which are coming from one type of scatter. Similarly, the other group is combined into a second type of scatter, and third group is also combined with the third one, and the fourth group would be combined with the fourth one, and so on. So they are combined to form an average value, and this type of profile is typically known as power delay profile. So different signals, they arrive at the different at the receiver at different times, and we combine them together to represent the power delay profile. This averaging is actually done in the same way as we generally do the averaging. So different the power associated with each scatter is actually average value of all the signals which are associated, the powers of all the signals which are associated with that particular scatter, and the average delay is actually the weighted average with respect to power associated with that particular delay. So this is how we create a power delay profile. This is a typical illustration of the mean power delay or delay spread associated with different types of environment. For example, we have a small office or home. So if we calculate the power delay profile, so we see that the signals arrive at different delays. So 0 is actually just a starting value, so we do not have any component at tau equal to 0. With a 0.31 microsecond delay, we see that the relative mean power is actually only -1 dB. With the signals coming with the 0.71 microsecond delay, they are associated with the power of -9 dB, and again, as I mentioned in previous slide, that it's an average value of that power. So this is average received power. So signals coming with 1.09 relative delay, they are associated with the -10 dB average power. Signals coming with 1.73, that is associated with the -15 power, and so on. Similarly, the same measurements were taken in some other type of environment, which is a large warehouse. You would see that again you can make a power delay profile. The power received is actually for 0 delay, the reference delay, the power received is -2.5 dB. For 0.3, the power received is 8.9 dB. The received power is -12.8. For delay of 12.9 microseconds, actually the received power is -10. 17.1 microsecond delay is associated with the power of -25.2 dB, and so on. So this is the power delay profile measured values at two different types of environment. You can see that as we increase the delay, the signals which are coming with the larger delay, they are associated with smaller amount of power, which is quite logical, as we discussed before, because the longer propagation is associated with the typically larger environment. But there may be some differences. For example, you can see a difference here, that at 17.1 you see a significantly large power. This thing happens in certain cases where certain other losses are associated. Say for example, if there is a obstruction in that particular path, so eventually, or partial obstruction in that particular path, or if there is a medium with higher loss, so in those cases we generally have this type of effect where you have large loss even with the smaller delays. So this is power delay profile in other type of outdoor environments. So if you take a typical urban environment, a hilly terrain, or a rural environment, in that case the power delay profiles are represented here. Again, these power delay profiles, they are on the basis of the measurements conducted by different researchers in different types of environment. So if you have an urban environment, you would see that the different delays, they are associated with different powers, which are listed here. Similarly, hilly terrain, you can have a power delay profile here. Similarly, the delay for rural areas, the typical delay profile is represented here. So typical delay spreads in different types of environment are mentioned here. For indoor cells, that we get a typical delay profiles of 0.01 to 0.5 microseconds. delay spread for open areas is less than 0.2 microseconds. For suburban areas, you can expect a delay spread of around 1 microseconds. For urban areas, it goes to around 1 to 3 microseconds, and for hilly terrain, it's generally 3 to 10 microseconds. I would encourage all students, because these power delay profiles are given, sample power delay profiles are given here, and for indoor environments the power delay profiles are given here. I would encourage all the students to try to calculate the delay spreads for these sample power delay profiles. So let us take a simple problem here. We want to compute the mean axis delay or mean value of the delay as well as the delay spread. So we want to calculate mean axis delay and the delay spread for a certain type of environment where you are giving this power delay profile. This power delay profile is given here. You can see that this time axis is actually representing the delays, and the vertical axis is actually representing the overall power which is received at that particular delays. So we want to compute mean axis delay and tau m for multipath figure which is shown here. So you can see that at 0 we have a delay 0 tau time delay. We have a received power of minus 20 dB. At 1 microsecond and 2 microsecond we have a delay spread of around minus 10 dB, and for 5 microsecond the delay spread is almost 0 dBm. In order to calculate the delay spread, because we need to calculate the weighted average, we need to transform these decibel values into the fractional values. So 0 dB when it's converted to watts, so it will be representing 1 watt. Minus 10 dB would be representing 0.1 watt, and minus 20 dB would be representing 0.01 watt. So these are the values, non-decibel values for the received power. So we know that first we calculate the mean value, because this mean value will be used in calculating the delay spread as well, and we also need to calculate for this problem as well. So mean value is the weighted mean of the delay. So weighted mean means we are calculating the mean with respect to the power, which is stated here, a square ti. Ti is the individual delay and ai square is the mean values. So ai square, you can see for 0 delay ti, when the delay is 0, the mean power is 0.01. So you can see that for 0 ti value the mean power is 0.01, and in denominator you get 0.01, plus for second term the mean delay is 1 and the received power is minus 10 dB, which is equal to 0.1 watt. So for delay of 1 unit the mean power is 0.1, and because we have two such values here, so in denominator it's mentioned it's 0.2. Similarly for third sample the mean delay is 2 and the received power is again 0.1, 2 into 0.1, and similarly for third one the mean delay is 5, but the delay is 5 and the received power is 0 dB, which is 1 watt. So this will be represented as 5 into 1, and in denominator we have sum of all the powers. And if we simplify this thing, we will see that the average mean delay is only 4.38 microsecond. Second thing that we need to calculate is the mean square power, which is actually mean value of the square of the delays. So it's again calculated in the same way, but in this case we have to multiply with the square of the delays. So all the rest of the stuff is same, but we have to multiply with the square of delay, 0 square, and this is 1 square and 2 square and 5 square. So in this expression, wherever we have used the delay, we are now using the square value, and rest of the stuff remains the same. And if you simplify this thing, so we would see that this comes out to be 21.07 micro square and microsecond square. And we need to calculate the delay spread as well. So if we calculate the delay spread, so this is standard deviation, so we simply use the formula of standard deviation, which is the under root of this mean square value minus square of the mean value. So square of the mean value is 4.38 squared, and mean square value is 21.07. and if you simplify this thing, you would see that the delay spread comes out to be 1.37 microseconds. Okay, let me quickly go back to this previous slides. This delay spread in coherence time is generally taken as 1 upon Tm, but this is a conservative approximation. Sometimes for more stringent approximations, we use another formula for that, which is actually delta Fc is approximated as 1 upon 5 times Tm, which is, or 0.2 times Tm. So this is another approximation which is used in certain scenarios. So for this particular case, we have used the second approximation, delta Fc is equal to 1 upon 5 Tm, which gives a coherence bandwidth of 146 kilohertz. So this particular delay spread is associated with the 146 kilohertz. Okay, now we come to the second part of the problem. Specify whether an equalizer is needed for EMS and GSM signals. GSM signal, they have bandwidth of 200 kilohertz, and EMS signal were supposed to have bandwidth of 30 kilohertz. So whether we need to have equalizer or not, first thing, you should recall that equalizer would be needed if there is a distortion in the signal, and distortion comes when the delay spread is large. In other words, the coherence bandwidth is smaller than the signal bandwidth. In that case, we would be needing equalizer, otherwise we would not be needing equalizer. So in order to determine whether you need an equalizer or not, you need to compare the coherence bandwidth with the signal bandwidths for different systems. So for EMS, the bandwidth is 30 kilohertz, and the coherence bandwidth is 146 kilohertz, and you can see that coherence bandwidth is significantly larger than the signal bandwidth is 146 kilohertz is much greater than the 30 kilohertz. In that case, for this particular scenario, we would not be needing any equalizer. But if we look at the GSM signal, which has a bandwidth of 200 kilohertz, and if we compare with the coherence bandwidth of the channel, in that case this coherence bandwidth is only 146 kilohertz, which is actually smaller than the signal bandwidth. And because the coherence bandwidth is smaller than the signal bandwidth, in this type of implementation you would be needing an equalizer to compensate for the distortion caused by the channel. And this distortion would be there because of this frequency selective nature of that particular channel. So this concludes our discussion on the delay spread and the coherence bandwidth. The delay spread is one of the physical phenomena which comes from the fact that the signals are propagating from different paths, and different components associated with different paths, they arrive at the receiver with different delays, and those different delays, they cause an average amount of the delay spread. The frequency domain version of this delay spread is the coherence frequency or coherence bandwidth. Coherence frequency determines how much frequency channel possesses, or in other words, this is the frequency where different phase amplitudes, they are correlated with each other, and beyond that the phase amplitudes are uncorrelated with each other. Okay, so this concludes our discussion on this topic. So we now move on to the second type of phenomena, which is actually Doppler shift or Doppler effect. What is Doppler shift? If you recall from your pre-engineering studies, you would see that whenever a vehicle is moving and it's generating any type of frequencies, so the movement causes changes in the Doppler in the frequency of the signal, and that change in the frequency is known as Doppler shift. A common example in this scenario is that of an ambulance. Whenever is the case, because when an ambulance generates sound waves which have certain frequencies, and if ambulance is moving, the wave which you receive at the receiver side, they have certain different frequencies, but those frequencies, they are different with the frequencies which are generated by the siren of the ambulance. If the ambulance is coming towards you, you would see an increased frequency, you would observe an increase in the frequency, and if ambulance is going away from you, you would see a decrease in the observed frequency. The same phenomena happens in the mobile channels, because mobile signals, they are also associated with certain type of movements, and those movements, they are associated with this Doppler shifts as well. So whenever a mobile equipment is in motion, it will cause some change, some deviation in the frequency, which is represented with the Doppler shift delta FD. So say for example, you have a mobile equipment in a vehicle which is moving with certain velocity v, and you have a receiver which is represented here as at point S, and this vehicle is moving in certain direction. In that case, the phase change that we observe, as we discussed previously as well, this will be 2 pi by lambda multiplied by change in the length, whatever extra distance it needs to cover, delta L. And this delta L, because of using S into Vt formula, which is standard in the physics, so we would represent this delta S by V into delta T. But because we are observing this signal at a certain angle theta, so that thing would be represented as a cos theta, as we are looking at the projection at the horizontal axis. So change in the frequency is associated with the phase by this relationship. Fd is actually delta phi by delta t. Actually, in the limiting sense, this becomes d phi by dt and divided by 1 upon 2 pi. If we substitute this expression here, you would see that this change in delay would be v over lambda cos theta, and you can see that this change is dependent on velocity of the vehicle, which is v, which will be calculated in meter per seconds. It's also dependent on the wavelength, which is the wavelength of the wave which is generated by the transmitter or receiver, and cos theta is angle between the direction of motion and the arrival of the direction of RF energy. So direction of motion is this one, and arrival direction of this RF energy is this one, so this angle is theta. And again, this frequency shift would depend on the direction of motion. If you are moving towards the receiver side, in that case you will see a positive shift in the frequency. That means you would be having some addition, some higher frequency or increase in the frequency by virtue of this Doppler phenomena. And if the mobile equipment is moving away from the receiver, in that case there will be some decrease in the frequency, or we would see a negative shift in the frequency. So what we observe here, whenever the mobile equipments they are in motion, they are associated with some sort of delay, which is some sort of change in the frequency, which is represented as the Doppler shift in the received frequency of the received signal. Okay, it must note that the shift occurs in both cases. Whenever the mobile equipment which is associated which is in the car, it's generating the signal. In that case, you would be having some Doppler shift, and even in the case when the signal bounce from a car which is in movement or received at some other place, that type of signal also have some Doppler shifts. Doppler shift occurs in both ways. So in that case, the multipath signals, they also have certain Doppler shifts associated with that, because the signals, they are coming after bouncing from different objects which are in motion. So you would see that there will be different Doppler shifts associated to each of the multipath component. So this is the discussion related to the Doppler shift. So we will continue our discussion on the same topic, inshallah, in our next class. Thank you.